In this review, we study two problems. One is the arc length problem, and the second one is the surface area problem. So let's start with the first one, which is the arc length. Arc length. So let's say you have a curve, uh, just going from some point to some point. So let's say you can start with the value a and go all the way up to b. So if you can say your function is y equal fx, your goal is to find this length. So I'm going to call L. So let's try to find this length. That's what we call arc length. So you can see that without calculus, we cannot do a problem like that. So that's one interesting situation. Um, and then also later we can talk about what we call the arc length function. So what's the arc length up to value x? So, so what we have is, so we have y equal fx, which is given as a function of x. And we assume that the first derivative is continuous. So we can assume that the first derivative is continuous. Okay, let's assume that first derivative continuous, and then the arc length function is given by since L, which is going from a to b, the integral, and 1 plus. What's going to happen is you're going to take the first derivative and you're going to square it, and then add 1 and take the square root. So remember, you can cancel this square root and square because there's a plus 1 here, and then you can integrate this with respect to x, and this is what we call the arc length function. So what we do, we take the first derivative, you square it and add 1 and then take the square root. So what's going to happen is when you have a problem, you have to simplify this part. So we're going to look at that in 3 problems. So this is the first equation. So I'm going to call this equation number 1. And also sometimes we write the exact same formula like this. So it is L equal a to b 1 plus, so the derivative we write dy by dx. Okay, so maybe you like that, and then you square it, add 1 and take the square root dx. So what's going to happen is you need to simplify this. So that's the goal, like you try to simplify this part first and then try to the square root. So this can be complicated depending on the problem that you get. And then there's another one, what we call the arc length function. So what's the arc length function? Instead of you integrating from a to b, you integrate from a to x. So this is what we call the arc length function. So the arc length function, arc length function is simply, let's say it's Lx. I use L because it's the length. So it's going from, let's say, a to x. So we're going to find the length up to, so that means, so what we are talking about is this part. So what is the length from here to there? Okay, what is this length? So that's what you call arc length function. Then when you change x, you can get the value of the whole curve. So if you know the value at b, you simply evaluate this function at b. So then you're going to get from the value from a to b. Okay, so we write from a to x. A is starting value. So you the x coordinate. That's just the x coordinate of the point. Okay, so the actual point is whatever a, and then you have the value at here, which is y evaluated at a. So we don't worry about that, we only worry about the starting value because only the x value, because this is integral with respect to x. Good. And then this is just the same thing, but since we use x here, we are not going to use x inside. We use some other what we call parameter, let's say t. So make sure the u is something else like that, and then this is square root, and so it can be dx, it be dt. So just change the xt, what we normally call a parameter. So this is what we call the arc length function. Okay, arc length function. Now if you need the actual value, if you need the value, the whole length, what do? You evaluate this L at b. So then you're going to get the exact same one as before. Okay, so those are the formulas that we kind of need for this one. So what we can do, we're going to do a couple of examples to see how it works. Okay, so let's start with the first one. So this is the first problem. So so let's say find the length of the curve find the length of the curve. So let's say y equal 4 minus x squared square root from 0 to 1. So that's x value going from 0 to 1. So let's try to do this. So you are given a function. Now we just use the formula. So what we know that when you use a formula, you have to do two things. First take the derivative and then evaluate 1 plus dy over dx squared. Okay, so let's do that. So the answer, so we have y equal 4 minus x squared square root. In other words, this is 4 minus x squared 1/2. That's going to be helpful. Now when you take the derivative, you have to use the chain rule. So let's use the chain rule. So this is 1/2 4 minus x squared and negative 1/2 times negative 2x. So this is coming from the chain rule. You know that you have to multiply by the derivative of the inside function. Here the inside function is 4 minus x squared. So you have to multiply by the derivative of that. Okay. So let's simplify this. So this is easy to simplify. You can see that 2 and 2 get cancelled. So you're going to get negative x over, this is negative half means square root. So 4 minus x squared square root. That's what you get. Now what we can do, we're going to calculate this 1 plus dy over dx squared. So this is always a good idea to simplify this first before you plug into the formula. That can save a lot of writing. So 1 plus, we're going to square y prime. So that means if you square, what's going to happen is this is going to be x squared over 4 minus x squared, because the square root get cancelled. Okay, that's what you get. So if you simplify, let's take the common denominator. Common denominator is 4 minus x squared. So if you multiply by 1, top and bottom by 4 minus x squared, you simply get 4 minus x squared plus x squared over 4 minus x squared. So you are in Calc 2 now, so you should be able to understand this step without any difficulty now. Okay, so these two get cancelled. So you get 4 over 4 minus x squared. That's what you get. Okay, now what you want to do is, now we can plug in. So we will take the square root. So let's plug into the formula. So formula says the length, the arc length. So the length, just say length, which is simply given by a to b 1 plus dy over dx. Always in exam write the formula, because you know, let's say you made a big mistake, but still if you write the formula you can get some points for that. Okay, now what I'm going to do, I'm going to plug in here. So a, the starting value, starting x value is 0. Okay, and it's go all the way up to 1. So it's 0 to 1. We know that this is 4 over 4 minus x squared square root now dx. So to get, now we can simplify this a little bit. So this is 0 1. So it's a 2 over 4 minus x squared square root dx. And you know that this is one of the familiar formula, is 1 over a squared minus x squared is the sine inverse x over a. So that's one of the formula that we have. So that means according to that formula is 2. This is sine inverse x over a in this case, because this is 2 squared. This is 2 squared. So that means x over 2. Okay, that's what you get. And then you can evaluate this at 1 and 0. So this is very easy to simplify. And you can see that this is 2 sine inverse. So if you apply x, so you get 1/2 minus 2 sine inverse 0, because when you plug 0 you get 0, but we know that sine inverse 0 is 0, so this is simply 0, because sine 0 is 0, so sine inverse is 0. If you look at the sine graph, it's very clear. Okay, when you go inverse, so you're going to go backward. You switch the x and y axis, so it's still 0. Same thing with tan inverse. Okay, so what is sine inverse 1/2? We know that the sine inverse 1/2, that means for what angle you get 1/2. You know that is pi over 6. So that means pi over 6. So, so you plug in pi over 6. So this is simply 2 times pi over 6. So in other words, pi over 3. So that is the length of the curve, pi over 3. Good. Now sometimes what they ask maybe like a what we call the arc length function. So if someone asks you to find the arc length function, what you normally do is you simply replace this b value b by x, and also change the variable inside to t. So let's do that. So if you do that, you can write it like that. So you can see, so let's say if you need the arc length function, arc length function, if you need the arc length function, so that is, we write this as Lx, it's a function. So what you're going to do, you can evaluate from 0 to x, and also inside you're not going to write x anymore, we write different variable, let's say t. So I'm going to change to t, switch x to t, and dt. That's what you do. So that's only change. You change the variable and put a x in there. So that's x, and then don't write x here, just put some other variable, what we normally call a parameter. So now this is the same calculation. So this is going to be t 2 times sine inverse t over 2 according to the formula, and then this is we have x to 0, and then you can calculate that, and you can see that if plug in 0 is 0, you get 2 sine inverse x over 2. So that's what you get for this, valid for any x between 0 and 1, because we did not consider any other values before. So this may be true for other values, but these are the values we are considering. Good. Actually this can go up to 2. Okay, good. So that's about that. So you can see this calculation is not that difficult, but there are certain things that you need to remember. Okay, let's do this example. This example number 2. So the problem says find a function for the length of the curve y equal 1/4 x squared minus 1/2 ln x, starting at the point 1/4. Where the 1/4 coming from? This 1/4 is coming from when you plug in 1 to the function. So you can see if you plug in 1 to this function, you can see that since ln 1 is 0, you get 1/4. That's the 1/4 coming from. That's normally unnecessary for a problem like that. And then it says that find the length of the curve for x from 1 to 2. Okay, x varying from 1 to 2. So what's the length of the curve that generate? So this is like a really nice function, but they ask in the function. So let's do that. So what we're gonna do is it's very similar to the previous problem. So we're gonna find the derivative first. So we have y equal 1/4 x squared minus 1/2 ln x. Now what we're gonna do is we take the derivative. So if you take the derivative, it is y prime, which is 1/4 times, what's the derivative of x squared? 2x minus 1/2 derivative ln x 1 over x. So you can simplify this. If you simplify this, you're gonna get x over 2 minus 1 over 2x. That's what you get. Now what we're gonna do, we're gonna find the 1 plus y prime squared formula. So we need 1 plus dy over dx squared. So let's plug in here, which is 1 plus, so it is x over 2 minus 1 over 2x squared. So how do you square this? Maybe you remember one of the formula that we know. So which says that if you have a minus b squared, which is you square the first one minus twice the product plus square of the last one. And if you have plus, which is a plus b squared, which is a squared, only change the sign. So ab, and still the last one has a positive sign. So you can see only the middle one change the sign. Okay, so this will be very useful. So that means according to that, which is 1 plus, you square the first one, which is x squared over 4 minus twice the product. When you multiply the two, x get cancelled and you get 4 in the bottom, but when you multiply by 2, you get negative 1/2 plus square the last one. When you square the last one, you get 1 over 4x squared. So you get and then you can see that, so I'm going to erase the this one, so let's remove it. So now you can see 1 and negative 1/2, you can simplify, you get x squared over 4 and be positive 1/2 plus 1 over 4x squared. And you can see that if you think of the formula that we just erased, that is exactly the top one but with the opposite sign now. So what you have here is, so you can see that according to the same formula but with the plus sign now. So with the plus sign, so what's going to happen now is, you can see this is simply x over 2 plus 1 over 2x whole thing squared. Okay, because the minus now changed to plus. So that's what happened. You can see this is minus, now we have plus. So only thing is sign change. Good. So that's a very good one. So this is what you always need to look for. See whether you can write this as a square. Okay, you need to look for something like that, especially for these kind of problems. See whether when you write 1 plus dy over dx squared, see whether you can write that as a complete square. Okay, complete square, like something like this. If you can do that, when you take the square root, that's gonna cancel out. So that's the whole point for this problem. So since we have it now, things are very easy. You can see now. So the length function. So the length function starting at the point 1/1/4. So you only need to pay attention to what the x value, because your integral is in terms of x. So E is simply Lx. We write this as Lx. So which is a to x. Okay, and then 1 plus. So I mean, when you write the formula, I'm going to write it like that, but be careful because this is just the formula. But we are not going to put x in there. Okay, we're going to use some other parameter. So let's say, so what time we'll do inside. So this is starting with 1 to x. Inside, I'm going to change this to t now, because cannot use the same variable as the limit. So I change x to t, 1 over 2t. Now we can see that, so this is a square and the square root. Since this is positive, and use of dt. Since this is positive, you can cancel out that square and square root cancel out. Normally what happens is, when you have a square, so I'm going to write this as a formula, what exactly happened when you have x squared square root, it is not x, it is absolute value of x. That's what you get. But since the function is positive in this domain, you don't need that. So you can simply say it is just the function, so it's 1/2 x, not xt, t plus 1 over 2t dt. I integrate from 1 to x. Now this is a very easy integral. So this is you can see it is t squared over 4 plus 1/2 the natural log t, and then you can evaluate this from x to 1. So if you plug in x, which is x squared over 4 plus 1/2 ln x. Here you can just say x because this is positive, minus, now let's plug in 1. So you plug in 1, you get 1/4 plus 1/2 ln 1. We know that the ln 1 is 0, so this is gone. So that means you simply get 1/4 x squared minus 1 plus 1/2 ln x. Good, so that is the arc length function. Now what we can do, length of the curve. So the length of the curve for x in 1 to 2 in that domain, what you want to do is x now is simply starting at 1, go all the way up to 2. That means you can evaluate at 2 now. So that means this is L2, so just plug in 2, so you get 1/4 2 squared minus 1 plus 1/2 ln 2, which is 3/4 plus 1/2 ln 2. So that is the arc length for the part where x changes from 1 to 2. Good. So let's do one more problem, and then we're going to move on to the surface area. So let's do just one more problem. So this is the example number 3. So they say find the length of the curve. So find the length of the curve y equal natural log cosine x from 0 to pi over 3. So if you look at this problem, so it's a very similar problem. So let's see how it works. But this is one of my favorite problem because it simplifies very well, and you need some knowledge of trigonometry also. So let's say we have y equal ln cosine x. So that means dy by dx, the derivative is by the chain rule, the function goes down and multiply by the derivative. So derivative of cosine means negative sine x. So this simplifies to negative tan x. Okay, because sine over cosine tan, but there's a negative sign. Now we can simplify. We know that 1 plus dy over dx whole thing squared is 1 plus dy dx is tan, so it's tan squared x. But we know from trigonometry 1 plus tan squared x means simply secant squared x. So this is one of the trigonometric identity. And then this is the formula. So the length is length L, which is a to b 1 plus dy by dx squared square root dx. So if you plug in, so you're going to get 0 to pi over 3 1 plus dy dx square. We simplify, this is secant squared x square root dx, but we know that in this domain this is positive, so that means it is 0 to pi over 3. You can simply cancel out, so you get secant x dx. And we know that the integral of secant means natural log secant x plus tan x. This is evaluated from pi over 3 to 0. So let's plug in the values. So if we plug in pi over 3, which is natural log secant pi over 3 plus tan pi over 3 minus natural log secant 0 plus tan 0. And we know that the tan 0 is 0 and secant 0. But we know that the cosine 0 is 1. Since the cosine 0 is 1, secant 0 is always 1 because it's upside down. And the tan pi over 3 is square root 3 secant pi over 3. For secant, let's find the cosine pi over 3. We know that the cosine pi over 3 is 1/2. So therefore, secant pi over 3 has to be 2 because upside down. Now, we also know that the ln1 is 0. We know that ln1 equals 0. So that means, yeah, actually we made a mistake here. This is secant 0, which is 1. So you get ln1. ln1 is 0. So that means this whole term is gone. So you only end up getting natural log 2 plus square root 3 as the length of the curve. And you can see that this problem simplifies very well. So this is like really nice problem. I like this very much. Okay, so that's about that. So we solved 3 problems. Now I'm going to give you a problem for you to try. So you can try this problem. So let's see exercise. Find the arc length function starting at the point of y equal, let's say sine inverse x plus 1 minus x squared squared. It's a nice function. So what it says, find the arc length function starting at the point 0, 1 of y equal sine inverse x plus 1 minus x squared. So see whether you can do this and get this answer. So the answer has to be the arc length function we call Lx, it's a length, 2 square root 2 1 plus x square root minus 1. So see whether you get this as the answer. Okay, so now so what happens sometimes so here what we have is y is given as a function of x. How about the other way around? So let's say if we can say if the curve is given as a function of y, as a function of y, so let's say x which is given as a function of y. So if this is the case, what we can do, we simply switch the order. So we can write the length curve. Let's still use the same letters, but instead of y over x, now we do x over y. So dx over dy. So that's the only change. So this pretty much you take the derivative upside down. So because in this case x is given as a function of y, and then you have to integrate this with respect to y variable. Okay, because dy. So it's a remember, it's a dy and dy. Good. So that's exactly what happened when you try to change the order. So so in this case, what happened is x is given as a function of y. Okay, so that's about that. So let's try to move on to the areas of surface of revolution. Okay, so let's discuss that. So what we can do is area of surface of revolution. Area surface of a revolution. Area of surface of revolution. So let's say so you have a curve. Now what we can do, we can rotate this about the x-axis. Okay, so when you rotate this about the x-axis, so what's gonna happen? It's gonna go like that, and this side is go like this. It's gonna create a surface. So you can see it's create a surface. Now what we're trying to find, we've tried to find this. What is the surface area? Surface area. So what we pretty much need is the y coordinate. So the y coordinate. And then you can see this curve is given as a function of x, so y equal fx, and then this rotate about the x-axis. So the surface area formula, so I'm going to write it. So the surface area is given by, we write S with the surface, which is a to b. So we have 2 pi y, the height y, and then we have the exact same from the previous the length curve. So you can see this is exactly same here, and then you square this square root. So that's the exact same term appearing here as well, and this is dx. Okay, so that's the formula for the surface area. So look at the remember the formula. So what happened is you have this extra term coming here, the 2 pi y term. So that's the only extra term, but that's just the previous one. You just added that extra term. So that's about that. Now, so what if you rotate about the y-axis? So if you rotate about the y-axis, so let's say if rotated about the y-axis, rotated about the y-axis. Okay, if rotated about the y-axis, so what's going to happen is you can see so slight modification. So let's say you have a curve like that. So now we can rotate about the y-axis. That means this part can jump to this side. So that means this is gonna go like that. This is gonna go like this. Now what we need the x coordinate instead of the y coordinate. Now we need the x coordinate. So that means you simply replace, and the length we can still keep that because it doesn't really matter whether you for the length you can still do the same one with respect to x or with respect to y. So that part doesn't change. Only thing is the x coordinate. So that means you simply replace the formula. So this 4, if you rotate about the y-axis, so it's going from c to d. So let's call it c to d, c to d. So it's c and d. So this is 2 pi. Now the x coordinate. The length is still the same, so we can replace. We leave it like that. So it's a dy over dx. And this is a dx, so it's a dx. Okay, so only thing that you need to remember is it only change this part of the function. Okay, so if we rotate about the x-axis, you have a y term here. If you rotate about the y-axis, you have x term there. This part is the same, so you can see that this part is the same along with the dx. So this whole part is the same. So you can see this is the same. So but what if, so here we assume that the derivative, you can integrate the derivative function is continuous. Dy over dx is continuous. That's the only assumption here. So if it is not continuous, what we're gonna do in this case, you can switch this. So if this is not continuous, we're gonna make it upside down and see whether that function is continuous. So what in that case, what's gonna happen is you simply replace that function by this function. So we can have 1 plus dx over dy squared square root, and this is dy. So we can replace simply that part by this if the dy over dx is not continuous. If not continuous, but if dx over dy is continuous, we can replace that. So that's the only one, but otherwise it just stay the same in the two cases. So if you rotate about the x-axis, you have y. If you rotate about the y-axis, you have x. Okay, so let's do maybe just one problem just to see how it works. So we can try this problem. So let's do this. So the problem is the arc of the parabola y equal x squared from 1 1 to 2 4 is rotated about the y-axis. Now it is rotated about the y-axis. Find the surface area. Find the surface area of the resulting solid. So this is clear. So but let's draw a situation here. So what we have is, so we have a parabola, part of the parabola which is going from 1 1 to 2 4. So this is the part. So it's going from 1 1 to 2 4, 2 and 4. So what we can do, we can rotate about this about the y-axis. So when you do that, you can see this part gonna jump to the side like that. So you're gonna get this, and you're gonna get that. So that's what you get. So they ask you what is the surface area of the resulting solid, and then you know that you only need the x coordinate in this case, and we also know the values going from here. So let's write it. So and then it's up to you whether you're gonna write an integral with respect to x or you're gonna write an integral with respect to y. Only need to consider what are the limits of x. So let's write an integral with respect to x. Okay. So we have y equal x squared. So y equal x squared. So that means dy over dx is 2x. This is a nice continuous function. So that means 1 plus dy over dx squared. You always need to simplify this part. It is 1 plus 4x squared. So let's write the formula. So the formula is s. Let's write an x integral. So which is a to b 2 pi x and 1 plus. So this is up to you what you're going to write here. Let's write the x1 because this is a nice continuous function. So it's a dx problem. So that means you need the x limits. So it is, what are the x limits? You can see the x limits are 1 to 2. Those are the x limits. So we're going to put 1 to 2, 2 pi x, no changes. And then 1 plus 4x squared square root dx. That's how you get. So you can see this is a very simple integral because the derivative of the inside function is 8x. We already have x there, so we need to create 8. So that means we're going to multiply by 4 inside and outside. So that means it's going to be 1/4. So we can write it like this. So so we can pull pi out and then divide by 4 and multiply inside by 4. You're going to get that, and 1 to 2. And then we also write this one as 1/4 x squared. And you can see that this is a you can also use a substitution for this part. You can just pick this one as u, but we can use a 4 formula trick because right now that's the derivative, so it's already there. So that means you can simply treat the inside function as x. So that means it's going to be 2/3 1 plus 4x squared 3/2 evaluated at 2 and 1. Okay, so if you do that, you're gonna get pi over 6. If you plug in 2, you can see that this is 4, 2 squared means 16, plus 1, 17. So you get 17 3/2 minus, if you plug in 1, you get 5 3/2. Another way to write this one is, you don't have to, but you can. So you can say 17 square root 17 minus 5 square root 5. So that is the answer for the problem. So this is the end of the arc length and the surface area problem, and those problems are very similar to problems like this. So what you want to remember is you need to understand whether the derivative function is continuous. If the derivative function is continuous, if the derivative with respect to x is continuous, then we can use the x formula. If the derivative is not continuous, we try the other one. We try dx over dy and see whether that is continuous. If this is continuous, then we can write an integral. Instead of x integral, you write the y integral. Okay, considering this one. So we consider this one in that case, because the both gonna give you the length curve, so it doesn't really matter which one we use. So depending on what is continuous, that's the only question we need to think about. Okay, so that's the end of the first review part.